I'd like to welcome everyone. My name is Larry Arthur with the Indiana chapter of the ACI. I'm the president currently. Today we're going to hear from Mike Collins of Lehigh Cement. He's going to cover characteristics of cement, types, and uses. There's a great wealth of knowledge here from Mike, and I want to let everybody know that we will be recording this and it'll be placed on YouTube at the Indiana chapter of the ACI's website. So all you have to do is log on at any time to be able to see anything that's covered here. If you're receiving a PDH, you'll receive them within 5 days via email. I'm going to turn it over to Mike. Mike has been doing this for numerous years, and he is a wealth of knowledge. Please hold your questions to the end and ask them then. I'm asking everyone to mute their microphones now so Mike can get started. Mike, thank you very much, sir.
Okay, thanks, Larry. Just want to say hey to everybody. Appreciate the chance to come and share. One of the tasks that's kind of before me is to understand just the breadth of experience that's in our group. So, I kind of got a little intimidated earlier. I saw Dr. Jan Olick has logged on, so I've got someone from Jan Olick, maybe on down from that. So, one of the goals that I try to have in a talk like this is to make sure everybody leaves here with something. And so hopefully that'll be the case as we go. And so, okay, is it going to work for us, Larry, or no? Okay. So one of the things that I try to do whenever I'm invited to speak is just at the very start of the talk, leave a little bit of leadership knowledge behind. And Ray DeLeo makes a quote that I think is pretty appropriate for this Indiana ACI meeting. He says, 2 people who collaborate well will be about 3 times as effective as each of them operating independently, because each will see what the other might miss. Plus, they can leverage each other's strengths while holding each other accountable to higher standards. And so what I've really come to appreciate about Indiana ACI as they host these monthly webinars is they give us a chance as an industry to get better together. I think it's really clear that we want to see the concrete industry move forward, and by coming together in webinars like this where we can all share some things we've learned along the way, it makes us all force multipliers, is how I like to see it. So I think it's a wonderful opportunity, and again, I appreciate the effort that Indiana ACI has done to put these monthly webinars on in a year that I think we'd all agree is just pretty whack. So today, what are we going to cover? We're going to talk about standard specifications and types of cement. We're going to walk through the quality control process at a cement plant. And that's going to be kind of a 30,000 foot overview. And then I want to get into mill test reports just a bit and kind of break those down so that everyone can see the cement properties and cement testing involved in what comes out on that monthly mill test report that you might receive from your powder supplier. So before we begin, just a little background refresher on some chemistry lingo. These are the basic elements that we're really kind of concerned with today. And along with the minerals that are formed during the pyro process, as well as the cement hydration process. So I don't want to overwhelm anyone with chemistry. It's not going to be, knee-deep Jason Weiss kind of level, but it is going to use some of these things as we talk about how they contribute to cement properties. Okay, so to get us kicked off, got a quick quiz. Portland Cement A was named after where it was first made in Portland, Oregon. B was named after the hometown of the man who first patented it, who lived in Portland, Maine. Or C got its name from a stone it resembled on the Isle of Portland off the British coast. And so if you said C, you are correct. Portland Cement gets its name from a stone it resembled on the Isle of Portland off the British coast. And so with that, we'll jump right into standard specifications and types of cement. And to do that, that means we're going to step into the world of ASTM for a bit, specifically going to look at ASTM C150, the standard specification for Portland cement, ASTM C595, the standard specification for blended hydraulic cements, and then ASTM C1157, the standard performance specification for hydraulic cement. And so as we look at the different types, starting with C150, ASTM defines Portland cement like this. They say a hydraulic cement produced by pulverizing clinker consisting essentially of hydraulic calcium silicates, usually containing one or more of the forms of calcium sulfate as an interground addition. Now, at the end of the day, I'm a pretty simple guy, and I understand things best when I can put it into street language. And so what ASTM is telling me here is that Portland cement is a powder made from grinding clinker and gypsum, and that powder gains strength when it gets wet. And so within C150, there's 8 main types of cement, and we also have, in addition to that, type 1-2 cement. So we have type 1 cement, which would be called the normal cement, type 1A, normal air and training, type 2, moderate sulfate resistance, type 2A, moderate sulfate resistance, air and training, type 3, high early strength, type 3A, high early strength, air and training, type 4, low heat of hydration, and type 5, high sulfate resistance. So when we talk about type 1-2 cement, that's a cement that would meet both the requirements of type 1 cements and type 2 cements concurrently, and that's being offered as suitable for use when either type of cement is desired. And so those A's here, when we look at this list, those are designating the air and training cements. I've been with Lehigh 32 years. When I first started at our Mitchell plant, we did make an air and training cement. And so what that meant was when you bought the powder, you didn't have to put air and training admixture in. It already had that built into it. But then as specifications became a little more diverse and there was different air ranges that you might want to provide concrete to meet, that kind of fell by the wayside. And it probably, gosh, I bet it's been 30 years since I think we probably made a 1A cement here at Mitchell. So you don't see those much anymore, but still something that's discussed. So these are the 4 main types of cement that we might see in kind of this Indianapolis, central Indiana, southern Indiana area, northern Indiana. Type 1, type 2, type 3, and again, that type 1-2 cement that offers the performance of both the type 1 and type 2. So that would be the main ones that we would deal with. Just in some general applications for some of these cements to kind of refresh our memory. Type 1, would be more of a general purpose cement, would be something used in flat work, bridges, paving, masonry units, concrete pipe, precast. Any of those applications might be suitable for a type 1. In terms of type 2, it can be, again, a moderate heat or a moderate sulfate cement. So in terms of moderate heat, might see that in bridge abutments, retaining walls, a concrete pier, something like that, where you're starting to get into more of a mass concrete situation. But also you might see a type 2 specified on a project where you need moderate sulfate resistance. So that could be any kind of drainage structure, sewage treatment facilities, wastewater treatment plants, something of that nature might call for a moderate sulfate cement as well. And when we're talking about type 2, typically we start to think about that C3A. It's a tricalcium aluminate phase, and that the content of that C3A is the main control factor with type 2, and it's limited to 8% maximum. So we'll kind of unpack that when we get to the mill test section. Type 3, high early strength cements, absolutely something that we're starting to see now put into application this time of year with cold weather concrete. Also a lot of precast pre-stress where forms need to be removed quickly. Post-tension concrete could be type 3 use. Any kind of pavement where that's a fast track or where that's a high traffic area that needs to be put back into service quickly, or a lot of times we'll see even still some concrete masonry products, again, especially when that has to be turned around quick or we're concerned with chippage on corners or something like that on the fine detail work, that might be a place for type 3. And then type 4 is a low heat cement. And again, this is a situation where we're looking at a cement where we're concerned with the heat generated from just the overall mass of the concrete, where thermal cracking becomes an issue. We can limit that amount of heat generation by the use of a type 4 cement. And bearing in mind that mass concrete, according to ACI 301, suggests that a concrete member with a minimum dimension of 4 feet should be considered mass concrete. Type 5 is a high sulfate resistant cement. This would be something that would be especially prevalent in the Southwest United States, where there's an abundance of sulfate in the soil. Could be something used around saltwater where we might have exposure in that environment. And I take that pretty seriously. So here's a picture of my wife and I. And if you've ever been to Key West, I bet you got a picture just like that where you're at the southernmost point. And if you've ever done that, you know that there's a really long line to step up there and get your picture. Like we waited almost an hour and a half in the heat down there one day to get our picture there. So if you're also like me and you're kind of a concrete nerd, you spend a big part of your vacation walking around with either your head down looking at the concrete or you're looking at the concrete poured around you. And so that's what I'm doing as I'm standing in line. And so what I found was that the overspray, when the waves get kind of stirred up and it can get a little rough around this southernmost point, you could see on this concrete light pole where the expansion started to really kind of kick in, and they tried putting metal bands around that to hold it in the best they could, but there was entire sections where the concrete was just gone. The good news is they're replacing those. You can see there, on the pole on the left of the first picture that they're actually trying to replace those. So I don't know how many times I've ran into buildings because I've walked around with my head down, but if you're like me, you've done that before. Just real quick while we're in the neighborhood, thought I would just mention white Portland cement. And you can get a white Portland cement in either a type 1 or a type 3. And the whiteness is a function of chemistry primarily, very, very low iron content. It's a special process, a special kiln. Not every cement plant can do that. So it tends to be a little more expensive because it's a matter of scale and a little harder to get. So it's supply and demand issue. But again, just a function of the iron content, and we'll talk about why that would be the case here in just a bit. Okay, so let's step into ASTM C595. That's the standard specification for a blended hydraulic cement. And the text definition says a hydraulic cement consisting of 2 or more inorganic constituents which contribute to the strength gaining properties of the cement. And so when we're looking at C595, we could be combining our clinker with gypsum, Portland cement, limestone, fly ash, slag, silica fume, calcine, clay. So we're taking 2 things now from an inorganic perspective and blending those or intergrinding those. And why I think it's significant to do that from a cement producer perspective is because when we make it on our end, when the cement producer makes this blended cement, we're optimizing the SO3 content. And that's really important because the SO3 that cement brings to that concrete mix, I think it helps us to understand we're talking no longer about constituents, we're talking about a system. So our concrete becomes an overall system where there's different components working together. And so the cement brings SO3 to that mix when all those things go into solution. And we're asking that SO3 to control a lot of different reactions. And so the cement producer is going to optimize that SO3 content on his end. And that is something I think that's going to be of benefit to controlling consistency of mix performance down the road. Looking at C595, again, blended hydraulic cements for general concrete construction. There's type 1L, which is a Portland limestone cement. Type 1P, a Portland pozzolan cement. Type 1S, Portland slag cement. And type 1T is a ternary blended cement. So we can actually blend more than those 2 items. And I wanted to just take a second and talk a bit about type 1L Portland limestone cement because unless you've been living in a cave for the last year or so, it's become more and more prevalent to hear about the green world. And so green concrete is a part of a greener world that we're all living in. And so I wanted to talk about a way that we can address that from our industry. So looking at Portland limestone cements, they are, again, called out by C595 and AASHTO M240. To make a Portland limestone cement, you can have a limestone addition rate of 5 to 15% limestone. They've got a pretty long history of use, started in Europe in the mid-60s. Canada kind of jumped on board around the start of the 2000s. And then the US jumped in earnest probably sometime between 2005, 2010, but really very prevalent from 2010 on. There's a few different mechanisms as to why type 1L Portland limestone cement works. 3 of the primary are particle packing, nucleation, and chemical reactions. And when when you use a type 1L cement, what we have found from our testing is that you can pull a type 1 or a type 1-2 cement out of your mix and typically replace that at a 1-to-1 rate with a type 1L, and you're going to see equivalent or perhaps even improved performance in just about every category that would be of concern to a producer. And really, the highest benefit, I think, going forward is that using Portland limestone cement provides an option to make greener concrete. There's a potential for 10% reduction in CO2, and that's all accomplished without any special system or addition to a ready mix plant. There's no hardware that has to be installed or anything like that. It's simply swapping your powder out from a type 1 or a type 1-2 and replacing that with the type 1L cement, and you begin to realize that 10% reduction. So I wanted to talk about that just a bit on why we see some of these performance enhancements from the Portland limestone cement. And one of the big ones is when we look at the particle size distribution of a PLC, you can see that on our red line here, that's the particle size spectrum of limestone powder in that mix. And what it does is extend the particle size distribution of the Portland cement more toward that very fine end. Portland, or the limestone, is very soft, so it grinds a lot easier than the clinker that is produced through a kiln actually does. And so it actually, you end up with a higher fineness material, but that higher fineness doesn't change the overall water demand or slump performance of that concrete. And so a good benefit of that fineness increase is that the higher surface area of the fine limestone provides surfaces for silicates to form and grow through a process called nucleation. So essentially it gives more places for that hydration reaction to begin to start. Wanted to talk about a couple of case studies with Portland limestone cement. One is at our, this is Lehigh's LEEDS, Alabama plant, and in 2008, we poured a new silo there. It was made out of a PLC slag combination. And so wanted to share some data from that. And pretty much true to what the industry literature says, you know, you can scour, PCA has all kinds of information about PLC and their performance. And typically what you're going to find is that there's a bump in the early strengths, and those strengths will kind of tend to equate with more of the type 1 strengths at 7 and 28 days. And that's kind of what they saw when they did the LEEDS project. You can see the green line here is the type 1L data, just a bit stronger at equivalent cement rates in their trial batches. And then at 28 days, you can see that tends to kind of close up a bit, but again, good performance from the type 1L cement. A little closer to home, we had a project back in September of 2020, just a few months ago, on I-65 patching, where some Portland limestone cement was used, and that with some good performance, I think. So we saw a 425 flex PSI spec to open to traffic with maturity that was reached in about 12 to 15 hours. The 3-day flexural spec was 625, and the average for that project was about 730 PSI in the 3-day break. So again, I think you see a little bump on that early side that tends to be very beneficial with the Portland limestone cement. And then just from Lehigh's perspective, I think most of you might be familiar with the fact that Lehigh's going through a $700 million expansion at our Mitchell plant. We're so confident in Portland limestone cement that about 95% of the structural concrete that's going to be placed for that is going to be Portland limestone cement. And so I wanted to share some things that we've learned from some testing at our concrete lab in Mitchell, Indiana. And these are just some generalities that we've kind of discovered some trends across different testing, different plants production as we've looked at this from 4 different Lehigh plants now. So in terms of strength, again, a slight bump at 1 day. Typically, those tend to kind of moderate a bit at 7 and 28 days and equal more of the type 1 or the type 1-2. What's been interesting, water demand is the same as type 1-2 or even reduced a bit. And we've seen slump loss improved in most cases, and workability is extended. We ran slump loss out to about an hour and saw that typically showed some value or some promise there with the PLC. Set time at 70 degrees has been neutral within about a plus or plus or minus 15-minute window versus type 1-2 cements. Admixture dosages in terms of water reducer, that's been almost 1-to-1 straight up across the board. Air entrainment, because of the fineness of the PLC, you might need another quarter to half ounce, maybe something like that, of the air entrainer dosage rate. That may need bumped slightly. Color, if you look at PLC under glass with that plant's equivalent type 1 or type 1-2, the PLC is going to be a bit lighter. You've got about 6% more limestone in that cement. And in terms of concrete, though, once you put that with that concrete sand, it kind of washes that color difference out, and there's really not very much difference at all. Shrinkage has been nearly equal, dead on equal with the type 1-2 mix, and something that we found to be a potential benefit is the PLC typically reduces the overall bleed rate. Again, I think that's a function of that fineness that we see. And so before we leave, just a brief discussion on PLCs, I wanted to share the latest map. PCA sent this to me in September. This is accurate at least through September 2020. And so you can see of the, the main continental states and even Alaska now, everyone but Hawaii is at least considering the use of limestone cement for state DOT work. In Indiana, we've certainly accepted that. And again, there's a whole lot of green on there, and I think it's an appropriate color because I think this cement's going to have a place in moving our industry forward in terms of overall carbon CO2 reduction. Would encourage you, if you haven't seen this, PCA has released a separate website called greenercement.com. So that's greenercement.com, and they have more information than you can shake a stick at here in terms of just overall PLC, why it works, why it can help with durability, resilience, all and giving you that 10% carbon reduction overall. So great website to hang out, get a lot of questions answered if you have any more about PLC. And lastly, just two resources from the PCA that I think are great places to start if you want to learn more about these products. If you want to email me after this talk, I can be sure, and I'd be glad to send you PDF copies of that or the links to those. Okay, so let's jump back into our types of cement, and we'll talk about ASTM C1157, Standard Performance Specification for Hydraulic Cements. So 1157 is the first performance specification for hydraulic cement, and now we're talking about a cement that meets a physical performance test requirement rather than the prescriptive restrictions that we're used to on ingredients or cement chemistry that we might see in like C150 or C595. And so again, we have our 6 types. We've got type GU, which is general use. And what you begin to notice is that the 1157 cements kind of have their C150 counterparts. So type GU general use is roughly equivalent in terms of performance to just our everyday type 1 cement. Type AG, high early strength, again, similar to the performance we would get from type 3 cement. Type MS, moderate sulfate resistance, and type MH, moderate heat of hydration. Again, that's your type 2 cements and so on. And so we can kind of break it down like this, that when we look at C595 versus C1157 cements, C595 is prescriptive, so that specifies what the cement must be. In other words, there's going to be certain limits on chemistry or components of that chemistry that you have to maintain either over or under, and then there may be things like physical characteristics like the fineness limit or something like that you've got to bear in mind as you're producing the cement. But when you look at C1157, again, it's a performance specification, so that specifies what the cement must do. In other words, we don't care how it's made necessarily. We don't care what you had to do to make this powder to get it to do whatever it does. We just want to make sure that it reaches maybe a certain strength at a given age or a time of set and a certain time frame, whatever it might be. So it kind of frees up the producer to make a powder that's going to meet a certain performance criteria, not so much follow a cookbook recipe. So I wanted to jump out of cements and look at quality control and cement manufacturing. And really each step in this whole process is important in determining the properties of the finished cement. We start an analyzing process all the way back at the raw material selection stage. You go to raw feed, then to actual clinker, to the fresh cement, and then wrap up your testing with the shipping and field samples. And so really for a cement plant, it all starts here. Almost every place you see a cement plant, there's a hefty limestone source either on that grounds or very, very nearby. And so because of the abundance of limestone, we got to have an idea of how we're going to remove that overburden, how we're going to expand that quarry, what's that going to look like when we start to plan how to mine this material. And so one way that we do that is to take core samples where they'll drill down through the rock and they pull out these core samples, and that can reveal the chemistry as they go down through different layers of the sediment. And then a quarry plan could be put into place. And so you see the bottom left here, there's a map of a two-dimensional quarry plan, and that would be how the cement plant would choose to expand and bring material up for use in the cement manufacturing process. And so really, because of the evolution of technology, it really allows some kind of cool things. So now you can leave that world of that two-dimensional map, and you can actually make three-dimensional quarry maps now. And this can even allow for more precise, mining and extraction of the limestone from the quarry so that you get the material you need to make the quality of cement that you're shooting for. So every time I give a plant tour, one of the questions that I'm always asked is, can we see a quarry shot? Well, A, those don't happen as much as you might think, and B, there's no way that we can take a visitor there and be safe sometimes in doing that, at least meeting our insurance quota. So what I've tried to do is bring a shot to you. So this is a shot of a quarry. So I don't know if you can hear that guy saying do it again, but he's pretty fired up by the whole process. So once we've got our limestone, really that is the key ingredient to move us toward understanding the four principal oxides that comprise our cement or make up our cement. So from those oxides, there are four that are in particular needed. That's calcium oxide. We need it, and these are just rough numbers, 64%. Silicon oxide is about 22%. Aluminum oxide, somewhere in the neighborhood of 6%. Iron oxide, about 3%. So those would be the major components that are required before you can make cement. And then there are some minor components in the process. You have alkalis, sulfur, magnesium, and titanium. And so where you get those four major components can come from a variety of different places. You might get your calcium around here. Like I said, primarily it's going to come from limestone. That's one of the things that why you see cement plants in our area is because we're blessed with a lot of limestone deposits. Iron can come from different places. I've seen it come from pyrite and mill scale particularly. Silica, again, primarily sand. The alumina source, at least in the Mitchell plant, is shale. And sulfate can come from either pure gypsum, anhydrite, calcium sulfate, whatever that might be. You have to have that sulfate, and we'll talk about why in just a bit. And so when we take that rock from the quarry to the plant, we take that stone and we first reduce it to kind of softball size, then down to golf ball size, and then it's brought to the plant where it's stored. And then once we have it here at the store at the plant in stored condition, we take limestone and a sand to give us the silica, alumina, or something to give us our alumina source, and then an iron source. We take those four things and blend those. And they're ground, and we want to make sure at that point that we start to really control the chemistry. They're ground specifically to a fine powder, and at that point, that material is ready to go into the kiln. And just all along the way, really, chemical monitoring is tied to production. If you've never been into a cement plant, it's an interesting place to take a walk through. And so there's different ways to do that. There could be cross-belt analyzers that give you a minute-by-minute readout of the material that's going on a belt. There could be, these older situations here in those bottom pictures where those tables actually speed up or slow down depending on how much of the material is needed to get the particular element out of that for the production that you need. And so once the material goes into the kiln, that's where things really start to change. So burning changes that fine gray powder chemically into clinker. And clinker is kind of, we'll talk about what that is. Inside the kiln, it's hot, and it's going to be anywhere from 26 to 2,800 degrees Fahrenheit. In the bottom right picture here, you can see that our fine gray powder almost starts to look like lava now as it kind of comes down through there. And basically what we've done is disassociate all the chemical elements into their free nature. And so now we're going to see some recombining of that as this material solidifies after being melted. And so when clinker comes out of the kiln, it passes through a cooler, and that cooler tends to kind of freeze or lock in the silicate mineral growth. We don't want those minerals to grow too big because we want the reactivity from a smaller kind of well-defined clinker, our crystal, a silicate mineral. And so when we're looking at clinker, typically a 5/8 of an inch, that's the old guys at the plant will tell you that's kind of an ideal size for a clinker nodule. And then those go into some internal storage. We want to store our clinker inside and keep it free from moisture. And then from there, so we have clinker that we produce, and now we add our gypsum, and that gypsum is added to moderate the set of the cement once it's added to water. So if we didn't have gypsum when we ground our clinker, it would just flash set, and then it would be of no good to anybody. So basically at this point, clinker with gypsum added, about 5%, roughly something like that, is added to the clinker during finished grinding. And again, this is where from here now we're coming out with our final cement. And then once we have our cement ground, it goes to the different silos, and from the silos, it's either bagged or put into rail cars or put into tankers and then delivered to the actual producer. And so let's talk about the cement properties and cement testing a bit. And some things we want to talk about here is start with mill test reports. Want to move into chemical properties and then talk about the standard properties that we look at from a cement manufacturer standpoint in terms of chemistries and physical tests. And then we'll kind of wrap up with just some other properties and tests that might be available. So if you've never seen a mill test, this is a mill test from February of 2020 here at our Mitchell plant. And this is pretty much what they would all look like. They all have a little different font or a little different look to them, but by and large, they have the same information on them, and they have to have that same information on them because there's some things that are required to be shared here. So that's pretty much a standard everyday kind of mill test look. And so this is something you might think about for later. I mean, what is it you typically look at on the mill test? What is it that you and your place in this industry, what are you concerned with? And then if there's anything on that mill test you need more info on, we can certainly talk about that later. I can do my best to get you some follow-up information. So when we talk about the standard chemical properties of cement, there's some routine tests that we're going to do. And so when we're talking about those routine tests, we're looking at oxide analysis, loss on ignition, insoluble residue, potential compounds, and equivalent alkalis. And so you'll find those, at least from a Lehigh perspective, listed on the left side of the mill test report. We're just going to kind of walk through those and see where those come from top to bottom. So the oxide analysis, years and years ago, this was how oxide analysis was generated. And when I first started at Lehigh, we still did this on a daily basis just to make sure we didn't forget how. But you can take a measured amount of cement, and I can stand there and do some mad scientist kind of stuff and make stuff change colors and smoke and do all that crazy stuff. And at about 2 or 3 hours, I can give you a pretty solid, pretty accurate breakdown of the oxide composition of that cement. But in 2 to 3 hours, there's been a lot of cement made because those mills don't stop while I'm in here running this chemical analysis. So what just about everybody would do in these days now, they do X-ray fluorescence for their chemical analysis. And this is where we could take that same cement powder, and in about 5 or 10 minutes, we're going to be able to give you a very accurate, highly calibrated breakdown of the composition of that. So that's where your oxides are going to come from in terms of the data generation, would be X-ray fluorescence. And so once we have those oxides calculated, then we can start to do some calculated value work and put together the potential composition of the Bogue using the Bogue equations that's based on the oxide data we generated. And so that's where we're going to start to hang numbers on things like C3S, tricalcium silicate, C2S, dicalcium silicate, C3A, tricalcium aluminate, and C4AF, tetracalcium aluminoferrite. And so that sounds okay, but what does that really mean? So when we talk about how those particular minerals might impact our cement and the performance of that cement, C3S, often called alite, contributes to the primarily early strength gain, and that's 1 to 7 days. And as the C3S goes up, you could expect to see an increase in the heat of hydration as well. C2S, or often called B-lite, primarily contributes just to the later age strengths, and we're looking at 28 days and beyond kind of strength gains. So not a lot of heat from C2S early on, but that's where you get that kick that you're used to seeing at 28 days. C3A, or illuminate, and this contributes to very early strength gain. And again, now we're looking at 1 to 3 days. This is a source of the initial heat of hydration. And if this gets too high, you can impair your resistance to sulfate attack and lower the durability of the concrete that would be produced if C3A is not controlled. And so C4AF, or ferrite, little effect overall, but it does affect the color. So higher levels of iron, if you see a mill test that has an abnormal iron, high iron content, that would mean you're probably going to see a darker cement. So if you've seen some cements that are either very dark, that means they've got a lot of iron. If they're really on the light side, they might not have as much iron. But from a production standpoint, the ferrite does have a role in the kiln as it acts like a flux and helps everything to melt a little more efficiently and more completely. So that helps just the overall clinker mineral composition performance. And so one of the things that we're asked a lot when we do our concrete training events here at our plant at Mitchell is, well, why can't you make a cement that's high early strength and high late strength? Why can't we have our cake and eat it too? And so some of that is related to the generation of these oxides and how they impact those Bogue equations. So if I want to adjust my silica content, if I raise my silica content, my C3S, my early strength is going to go down, but my C2S is going to increase. So if I raise my silica, there's a good chance that I'm going to bump up my 28-day strength. If I raise my alumina content, I'm going to raise the C3A. So then I'm going to release a little more heat once the water hits that. My early strengths are probably going to bump up a bit, but I've got a pretty hot cement now. So that means I couldn't have a cement maybe that would go into a mass concrete application. But I'm also, while I'm raising the C3A, I would also be lowering the C3S. So I'm kind of trading off there. I'm raising some early strength gain with the C3A, but I'm losing some early strength performance by lowering my C3S. In terms of the iron content, I can raise the iron. When I do that, I raise the C4AF, so I'm going to make a little blacker cement, but at the same time, I'm losing C3A content, and now I've lost some of my early strength gain or the potential to generate heat. Lime is the big one. As I raise my lime, the C3S goes up and C2S goes down. And again, that means I've got an increase in early age strength, but potentially a drop in my later age strength. And you can't do this just without consequence, because if you have excess lime in the mix, that's called free lime, and that free lime becomes an expansive mineral. And then just a couple other oxides and their impact on the overall cement performance. Magnesium oxide, potentially expansive mineral if that gets too high. And SO3, again, this mainly comes from the gypsum, and this is required to control Sept. So if we continue down the left side of our mill test, we find the loss on ignition test, and that's determined by heating cement, then measuring the loss. So you just take a platinum crucible and you put in a 1.00 gram sample of cement, and you heat that at 900 C. And then after a specified time, you pull that out, cool it, weigh it again, and you're looking at that loss in the overall weight, what you started with versus what you end with after heating. And so typically you see that value somewhere between 0 to 5%. Higher values indicate extent of prehydration and carbonation, and those can be caused by storage, could be caused by leaky storage. You might have a tanker truck didn't have a lid snug down, or a rail car that doesn't seal properly, or maybe your silo has some kind of leaking system in it, or just overall contamination maybe the tanker carried something before cement that would be causing you an issue. In terms of where else you might see LOI data, anyone that deals with ready mix and buys fly ash, you're looking at LOI data on that material as well. And we know, higher LOI could be problematic. Okay, in terms of equivalent alkalis, and so there's the table at the very bottom from the mill test report, and that's a measure of the total of the sodium and potassium alkalis that's recorded as Na2O equivalent on the mill test. And this is something that effective in April of 2019, ASTM made that mandatory on all mill tests to be reported. And what you found at that same time is that technically there's no longer a low alkali cement. We used to say 0.6% and lower in terms of equivalent alkalis was a low alkali cement. And that's because at one point in time, we assumed that controlling the ASR, the alkali silica reactivity, used to be kind of up to the cement. If you had a low alkali cement, then a lot of folks thought you were good to go. But with the C1778 guide for reducing the risk of alkali aggregate reaction in concrete, the alkali loading of the entire concrete mix is really now what's considered when selecting the mix components. I don't think people that make a low alkali cement are going to stop making a low alkali cement, in my opinion, because that cement contribution to the overall alkali loading of the concrete is very significant. So I think if there was a need for it before, I think that need's still going to be there. It's just technically they no longer specify or call out that low alkali cement. Insoluble residue is a measure of the acid insoluble material in cement. And the insoluble residue is a measure of how complete the reactions were in the kiln. Could also come from contamination. Like again, if that tanker carried something like fly ash before he had cement in there, that fly ash could raise the insoluble residue count in your cement sample and cause you an issue, perhaps with a state DOT or something like that. I had to get a drink of coffee, sorry. Okay, so let's move into some of the physical properties of cement. And here we're going to look at things like fineness, setting time, soundness, air content, and compressive strength. And so the first up is the measure of fineness. And one way that that's measured is the 325 mesh sieve or the 45 micron sieve. And here is, again, we're just putting a 1 gram sample into that sieve. And you got to understand, when we talk about 325 mesh, it's not 325 mesh per square inch, it's 325 meshes per linear inch. So it's extremely fine screen. If you poured water into that screen with no cement, the water wouldn't go through that screen. That's how tightly woven the screen is. So you have to have a high pressure nozzle to actually wash this material with. And so you're kind of blowing that the fine cement through there, and you're looking at the amount retained. That's going to give you an idea of the overall fineness of that cement. We can also measure that same fineness by looking at the Blaine. That's ASTM C204. And to me, one of the ways so this is the container here, this middle picture that you would place your cement sample in to drop it into the Blaine surface apparatus. And so here's how I kind of look at that. If I've got type 1 cement that I'm placing into that cylindrical test measure, then that's about maybe how big those particles are. If I was going to put type 3 in there, they're much smaller and they're much more tightly packed together. And so what happens is the air pulls through quicker in a type 1 than it does a type 3. So a type 1 has a lower Blaine measure than type 1 does. If you look at that from a cement model, or actually kind of a paste model standpoint, type 1 would be on the left here at a 0.4 water cement ratio, about 300 Blaine. And you can see there's some porosity involved here. We can see some water, some bigger particles in that computer model. When we jump over to type 3 at the same 0.4 water cement ratio, much denser, much more well compact. There's not as much porosity through that, and that's a 600 Blaine. So we doubled the Blaine there, and you can see the impact of that type 3 on the actual model performance. ASTM C91 gives us the setting time information. And this, again, it's a time of set test for paste. Well, actually, we're making a mortar here out of this, and as the mortar stiffens, the needle will penetrate less So that's what we're looking at, and there's a point in there where that would reach initial set. So I wanted to spend a couple of minutes and just kind of start to talk about setting times and types of cement and what this all means, and then kind of move this toward a practical application. So again, I'm kind of a hands-on guy, and I like to visualize things that I can put my hands on, and it helps me understand things. So if I visualize my type 1 as a basketball, right, just a regulation basketball, I would find that the volume of that basketball is 448.9 cubic inches, or the surface area of that basketball is 283.5 square inches. So that would be my type 1. If I looked at type 3, just kind of trying to visualize something, let's say type 3, a grain of type 3 would be my baseball. And so the volume of a baseball is 14.1 cubic inches, and the surface area of that baseball is 28.3 square inches. So what I find here is that there are 32 baseballs could occupy the same volume as one basketball. And so if that's true, then the equivalent surface area is 32 times 28.3, or 905.6 square inches of surface area. That's 3 times as much surface area for my baseball for the same volume that is occupied by one basketball. And so what that begins to tell you about type 3 is ground finer. It's finer than type 1. And what happens is the particles are smaller. They're more like the baseball, not the basketball. And because of that, the amount of surface area is much, much increased. And that begins to affect some of our performance. And so when we start talking about set time, there's things like time and heat and the type of cement and the surface area and reactivity that all go into considering what that means. And so let's kind of try to put some of that together while we're in this neighborhood talking about set time. So these are adiabatic calorimeters. One is set up in our lab, and one was set up at a customer's facility where we were doing some work for them on site. And so we're going to generate calorimetry curves, and a calorimetry curve is a way to measure the heat released by the exothermic hydration reaction. And to me, so exothermic means exit. So that means heat's leaving the reaction. It's exothermic. So when you put water with cement, you start to liberate heat. You can start to measure that heat almost immediately. And so that's what we're going to do. And so if I take a type 1 cement and I generate a calorimetry curve for that, it's going to look something like this. And so I learned some things from this. If I look at the height of the curve, that's approximation of the early strength gauge. So typically the higher that curve, often the higher the strength that we see from that particular material. When I look at the slope or the steepness of the curve, that's related to the setting time. So the steeper the curve, typically the faster the set time. So what happens if I do a type 3 onto this? So I can overlay a type 3 curve over that type 1 curve. And when I do that, I see that the type 3 has a much steeper slope and it's a much taller curve. And so I start to, that's what we expect, right? We're paying type 3. We pay for type 3 to get that higher bump in early strength. We expect that to be stronger earlier. Why is that? Because again, it's a function of surface area. So now there's more surface area of those individual cement grains for the water to get to and begin that hydration reaction. And again, that's why you see that steeper slope, because the reaction are starting to happen quicker. And because it happens quicker, you start to see a need now for an increase in the gypsum content. So in almost every case, you're going to find that a type 3 would have a little more gypsum than that same company's type 1 cement. And that reason is because this reaction is going to happen much, much quicker, and you want to be able to control that. And so again, gypsum retards the set in that cement. One of the fallouts of that is that extra gypsum makes the type 3 cement a little lighter. If you were to take a pane of glass and put type 1 and type 3 side by side and just mash that with another pane of glass, you would see that the type 3 is usually just a bit lighter in color than the equivalent type 1 would be. And so this starts to get some real world kind of stuff here when we start to be able to take some of the mill test data think about what that's telling us, and then apply that to some laboratory data, we start to be able to see, yeah, that makes sense with what I've seen in the field, or that's why this did that in the field. So it's kind of cool for me to start to put all that stuff together, especially when you're able to work with a customer on a project. Back to our mill test, the Soundness Test, it's an autoclave expansion test, and that's where we're trying to determine the volume stability of the cement paste. Basically, you're taking these mortar bars, and you're going to make those bars and put those into basically a pressure cooker, and you're going to put them under high temperature and high pressure, which is going to accelerate any reactions that might be negative, and then you're going to pull those bars out and measure them, and you're going to measure the potential for that cement in terms of expansive material. So there's a measure for that on every mill test report. Air content is ASTM C185. This is a test performed with mortar. It's always important when you see this test that you remember that these results do not correlate directly with air content in concrete. It's not a measure of entrained air, it's a measure of entrapped air. So again, don't when you see that 8% or whatever it might be on there, don't panic and think that you've got air in your cement. Okay, so everybody kind of, I think when they look at a mill test report, their eyes just kind of drift to that right-hand column, and they want to see how strong is this cement? What's the cube breaks? What's the mortar cube strength? And that's ASTM C109. So you take a 2-inch cube, you make those, break those at 1, 3, 7, 28 days, and that's reported on the mill test. And again, here's an old PCA graph that actually takes some of that data and shows you how that responds in terms of type 1 versus type 3. And again, this is why you buy the type 3, because you get that initial bump, about 15% bump in overall strength, but tends to moderate a bit as it goes on. And a lot of times that type 1 might close that gap as your 28-day period goes on. So those are the tests that would be standard tests that really every cement plant laboratory would run. There's some non-routine testing that can be done in terms of heat of hydration. That's ASTM C186. And there's a couple of data pieces here, just looking at type 2 generates about 70 calories per gram, and type 4 would do 60 calories per gram. That makes sense. If you remember, we've got a moderate cement in moderate heat cement in type 2 and a low heat cement in type 4. And then PCA threw some data together. This was a graph of a bunch of 1990 vintage cements where they looked at compared to a type 1 cement at 100%. This gives you an idea of just how those different cements might perform in a heat of hydration test. Type 2, type 4, obviously lower. Type 3, again, we expect it to be a little hotter, and it was at 106% of the type 1. Density of cement could be measured a couple of different ways. There's either the Le Chatelier flask or the helium pycnometer. And so why is that important? The cement density is used every single day in mixed design calculations. And if that varies, that can also just give us a good heads up on we might have a potential contamination source of cement. Just in the everyday calculations for the work that we do, we accept 3.15 is just the tried and true number for your accepted density. I know some guys are doing 3.14. We stick with 1.5. Another value that might be requested, not on an everyday mill test, but would be bulk density. And really bulk density is defined as the mass of cement particles plus air between particles per unit volume. So in these two beakers, essentially you're going to pour you poured 500 grams of dry powder into both of those beakers. And then the beaker on the left was just vibrated slightly. And what you saw is that there was a consolidation of about 20%, just knocking the air out of that powder. And so that really begins to confirm for us that really when you measure cement, you have to do that by mass instead of volume for batching concrete. You can do the 3-2-1 on shovel scoops if you're filling a mailbox post hole or something like that, but it's not going to work overall in terms of ready mix production. Particle size distribution, really just a more detailed measure of cement fineness. And I always try to explain this to people like it's almost like an aggregate gradation curve. So it really starts to look at the microscopic components of a cement and break those down into their different different quantities. And you're actually starting to see PSDs now more in the everyday cement plants. That used to be kind of something special that we would ship off for analysis. Now you're starting to see that again more in the plant-to-plant use. Because hydration is an exothermic reaction, that means, again, it gives off heat. We can do some things like measure that heat. And so that allows us to do thermogravimetric analysis, differential thermal analysis, differential scanning, calorimetry. These are all things that that would be at a research lab or some kind of a national lab for a cement company. Probably not going to see these at an everyday cement plant. And here's just an example of what that might look like if you were to take cement hydration and map it on a heat versus time curve. You can see again that initial spike in heat generation, and then the gypsum starts to control that reaction, and thereon you can kind of go on out from there. In terms of microscopy, we talked about this earlier, but you know, Clinker microscopy provides a snapshot of the conditions inside the kiln. And so what we're looking at here is how well formed are the edges of these clinker minerals, because that gives us an idea again of the actual melt. Was it a thorough melt? Was everything thoroughly melted and recombined in the kiln? And then was that clinker actually cooled properly? Because we want to quench that mineral growth. We want to stop it before it becomes excessively large. And so what we're looking for here is that size of mineral. And so these kind of lighter yellow color, that's the A-light, that's the C3S that would give you the early strength. And these darker brown kind of crosshatch, that's the B-light, the C2S. And that's about 400 times magnification. We can even take that down to about 3,000 times with the right equipment. And again, we're looking at those at the angularity of the edges of those particular minerals. You can do things like take a look at the hardened cement paste. This is a picture on the left of 500 times and a picture on the right of 1,000 times looking at that cement paste. And then something now that, you know, computers have really helped, I think, a lot, made this possible is you can do virtual cement testing. What this does is allow you to kind of play on a computer model with different components to see how those might work out in terms of hydration phases and different aspects of the hydration reaction. You can look at that on a computer model before you go to the lab. You know, I think at the end of the day, we're all going to want to do lab work. We want to get to the lab and do our trial batches, but I think it helps if we can eliminate some things early that might not be good options for us. And so, having said that, we're at the end of our hour. That's about all I've got, Larry.
Mike, thank you. I'm going to open it up to questions if anyone's got any questions.
Hi, this is Jan Oleg. Can I ask a few questions?
Please.
Absolutely.
Mike, thank you for a great presentation. It's always nice to see somebody from the industry giving their perspective to supplement what we learned from the books. So I have 3 questions for you, if you don't mind. First one is, you mentioned that cements with the A are not routinely produced, not in Indiana. Are they produced routinely anywhere?
You know, not that I'm familiar with, but again, I'm more focused on a Midwest region, but I don't know of any in the Midwest region. That's a great question, and I can certainly try to find out if there's any within Lehigh for you.
Yeah, because I always get this question from the students when I discuss with them ASTM C150. And I said, you know, as far as I know, nobody makes it. So they say, well, why is it still in the spec? You know, it's easier, you know, even the students say it's easier to get the air entrainment by training admixture into your concrete rather than rely on cement when you have lack of flexibility with respect to that. But, you know, somehow it persists in the specification. So I don't know. But the second question is, you are talking about type 3 cement, and you are talking about grinding it, you know, to greater fineness. In some cases, actually, I would say in most of the cases, you will probably see differences in the amount of C3S for those cements, but in many cases you don't. So I wanted to know, what is the current industry practice? Is it cheaper to simply grind it finer and sell it as type 3, or do you actually, as a plant, try to make, let's say, type 3 during the winter months with a little bit increased amount of C3S?
Right. I think what you're going to find in most common practical production practices is that there's one clinker. You know, at least I want to say in my experience, I guess, that there would be one clinker. So one chemistry, you know, going into the kiln, effectively one chemistry coming out of the kiln. And so the only modification to that would be the finer grind and the addition of the extra sulfate.
All right, thank you. And the last question, you know, ASTM C150 has a set of equations for doing the bulk calculations, but my understanding is that plants very often use modified version of those. Could you tell me what is the current practice?
I can send you maybe an email about that.
Okay.
Is that okay?
Sure.
Okay.
Thank you.
Uh-huh.
Anyone else? Mike, I've got a couple questions. Alkali content of cement, why is that so important to the operation of the cement process?
Well, it's a function of your raw materials in most cases. You know, like at the Mitchell plant, the shale that we use, it would be very difficult for us using the current shale that we have to produce a low alkali cement. We're kind of, the Mitchell cement, I don't know if you saw on that mill test, I think it was 0.7. So it kind of walks that line. It's not quite low alkali, but it's lower non-low alkali, in other words. And so typically you're at the mercy of your raw materials on something like that. You know, and it can affect some things. I mean, low alkali, typically low alkali can often cause a reduction in early strengths, something like that. So it is something that you kind of have to monitor, but you know, you trade that off against, you know, the effect that it might have on ASR or something like that.
Okay. So can you explain a little more in depth what the loss of ignition is?
Basically, you're just driving off the water component. You know, there's water associated with in that, tied up in that chemically, and so you're basically driving that off. Could be if in terms of, you know, outdoor material or something like that, but the other thing you're also looking at is terms of the calcium carbonate. You're driving off that CO2 at that point, and that's going to allow you to get a measure of, you know, the limestone content or you know, something like that.
Okay. That's all I had. Anyone else have any questions?
Yeah, this is Josh with Wilhelm. I had to step away for a minute. I missed the first couple of questions there, so sorry if I'm repeating something. But other than color, what would be a reason for a type 3 cement to be rejected in a concrete mix? We've got a project where we're trying to get type 3 approved, and it was not, and I just didn't know what the concerns would be for that.
Was heat an issue?
They didn't say. We're trying to submit it for cold weather, and we submitted basically the exact same mix, same poundage, just switching from type 1 to type 3.
Right.
And it just was rejected with no comment. So I didn't know what the concern would possibly be.
Yeah, I mean, I would, you know, the first thing that there is going to be more heat generated in that concrete, and I don't know what the structure might be. But so heat's going to be a bit of a concern. You know, when you switch from type 1 to type 3, you're changing the water demand a bit because it is going to take more water. Or if you've got a cap on your water cement ratio, which you probably likely do, you know, now you're going to have some more, a bit more water reducer maybe to get the equivalent workability, but that shouldn't be a reason for, that would be something you would accept more than they would say not acceptable. So, I'm kind of curious. I would be curious to see their thinking on that as well.
Yeah, we've asked for additional information and, a reason for their rejection, but as far as I know, we haven't received that yet. So,
Mike?
Yep.
I don't know what his application is, and Jan could probably shed more light on this, but I know NDOT, there's such a thing as a sulfate imbalance, and NDOT is not allowing type 3s to be used in conjunction with accelerators. I don't know what his application is, but I do know we have concerns about using type 3 with accelerators. Jan can probably elaborate further on that, but that's our reasoning, and I don't know what his application was.
Yeah, I can only confirm, Mike, that based on some research that was done, among others, at Purdue, that a lot of accelerators bring in their own sulfates components, and if you have increased amount of sulfates in type 3, there is concern that there might be some issues related to compatibility of the admixtures, and that might be one of the reasons. The other reason is my thinking. If you react more of the cement, you produce more calcium hydroxide. So potentially, cement with higher amount of C3S, or if this is not the case, just more finely ground, it will still react more of the cement grains, presumably, right? So they will produce more calcium hydroxide, which might present some issues with durability when concrete is exposed to the icers. That might be another reason. On the other hand, if it's
that would
tighter,
seem to make sense. Yeah, it is a parking garage project.
okay.
Was there any SCM in that mix at all, Josh?
No,
That would even
I don't
kind of,
believe so. I'm trying to think. I don't think so. We've taken it all out if there was.
yeah, that would even more make me think, that de-icer issue might be where they're going.
Yeah.
Great questions. Are there any more? Mike, that was a fabulous job. Great knowledge. I would like to say that your presentation covered a lot of great topics, and what I really got out of it was good. But what you left me lacking on is the Portland limestone cement. At this point, I'd like to invite you back for another webinar in a couple months to actually cover more in depth of the Portland limestone cement. I think that's going to be a hot topic in the next coming years. So if you'd be willing, we'd love to have you back.
Absolutely, would love to.
So if no one has any more questions, I'm going to thank everybody for attending. I will get this finished up in a recording, put online for everybody to use as reference in the future. And thank you everyone for coming. Mike, it's always a pleasure.
Merry Christmas, everyone.
Merry Christmas.
Yeah. Thank you, Mike.
Mike, thank you very much. It was a great job.
Hey, I appreciate it, Larry. Appreciate the opportunity, and appreciate the chance to come back and talk about limestone cement.
I mean, it was a great presentation. You really left me with, I want more knowledge on the Portland limestone. So
well, we can do it.
Good. I think that'll be a very hot topic right there. So
I think you're right. I think you're exactly right. Well,
Thank
hey, thanks
you
for
very
the chance to come. I appreciate it.
anytime, sir. Thank you.
All right, brother. Take care.
Thank you. Bye.